Good evening from Johns Hopkins University Applied Physics Lab, where we have been hosting this ACM Baltimore seminars. This is the fifth one. I am Ashutosh Datta. I serve as the chair for Baltimore chapter. So hello everybody. I know this is being broadcast to people around the world. There have been some discussion about having the networking option. We will do that next time. I just need to understand exactly what you meant by that. Is it like talking? Maybe we can have a separate room. We have thought about it so that before the thing starts, at least you can have networking. That's something Jeff Chavis had thought about. We just didn't get a chance to implement that. So we'll make sure that is available next time. But at least you should be able to chat on the chat box. If you meant like a separate meeting, a room for networking, we'll do that next time. So with that, this is the, let me see if this is working. Yep. So hello everybody again, good evening, good afternoon, good morning. I know some people may be waking up, some people may be just going for dinner. We have the fifth seminar, and there are two talks today. 6G XR Metaverse, Silicon Valley View by Professor Misha Doller, and a dual blind deconvolution perspective of integrated sensing and communications by Dr. Bijay Mishra, Kumar Bijay Mishra. So they are experts in their own field. We'll go over the bio later on, but they're also distinguished lecturer for Future Network Initiative. And this has been organized in collaboration with IEEE Baltimore section, Computer Society chapter, IEEE Princeton Central Jersey section, and IEEE Central section Communication Society chapter. Faji Mevin, thank you for your help. Roger Ding, and Baltimore section where this is being held. That's me. I work for Johns Hopkins University Applied Physics Lab. I'd like to acknowledge many of my colleagues. Some of them are here, some are on the Zoom. Jeff Chavis, who is the Vice Chair, ACM Chapter Baltimore, Chapter of Baltimore, Randon Gwynn, the Webmaster, Tamim Sekur, Secretary, Kent Smith, Membership Development Chair, Wale Akinpelu, who will be here, who is here today on site. You have seen him. He serves as the treasurer. There are a few other people who have helped quite a lot. Ryan Pepito, who has been instrumental, and Mithun Mukherjee, who has helped with various things. And also like to thank all the folks at Hopkins, other volunteers, ACM Baltimore chapter, making this happen. So we typically have 2 talks for each seminar, and it's back-to-back, still doing in a hybrid mode. So there are people around the world can join, and folks here. We also wanted to thank ACM headquarters for helping us with the ACM meetup series. Andrew actually helped us out on that, so thank you. And Sunita from the ACM headquarters local activity for helping to circulate this as well. So Misha Dollar, VP Emerging Technologies from Ericsson, Kumar Bijay from US Army Research Lab. Just to give some ideas if you have missed, we had our kickoff on 24th of February, and we had the speakers, ACM, the then president, Gabriel, Dr. Ralph Semmel, director of APL, Professor Len Kleinrock, if you have read the queuing system, one of the fathers of the internet, or ARPANET, April Erickson from NASA, and Professor Henning Schulzerin from Columbia University. They were the speakers. This is already available, ACM YouTube. And then the second one we had on April 20th, Professor Stephen Ralovin, Dr. Anupam Joshi. This was purely focused on security. Third one, Professor Raj Jain from Washington University, Albert Greenberg, Vice President from Uber, and Milin Chabi, also from Uber. So that was interesting talk. That's also available. And the last one we had October 18th in 2022, Gabriel Waters. And I mean, he actually spoke about all the digital twin stuff. So that's also available. Some few glimpses of the pictures that they're all there. So this we are doing at the same place. We are also looking for alternate locations around Baltimore area so that we can have variety a little bit. If you know somebody, if anybody interested, please let us know. We've been talking to DISA also, find another place, maybe Johns Hopkins University, University of Maryland, Baltimore County or College Park, even Virginia Tech could be one of them. These are some of the glimpses. August 11th, this is where we met. This is the last one, October 18, that we had it here. These are the recordings of all the 4 seminars we had. Please take a look at that. I know people have been watching it. I'd like to thank ACM headquarters for putting this in up there. With that, I now like to welcome Wale Akinpelu, my colleague, to come and introduce our new speaker.
Thank you, Ashutosh. I want to welcome everybody as well to this 5th session. Our first speaker is Michel Dola. He's a VP of Emerging Technologies at Ericsson, Inc. in Silicon Valley, working on cutting-edge topics of 6G, metaverse, XR, quantum, and blockchain. Michel holds a PhD in telecommunication from King's College London that he received in 2003. He serves on the Technical Advisory Committee of the FCC and on the Spectrum Advisory Board of Ofcom. He's a fellow of the IEEE, the Royal Academy of Engineering, the Royal Society of Arts, the Institution of Engineering and Technology, and a distinguished member of Harvard School Leaders Excellence. He's a serial entrepreneur with 5 companies, composer and pianist with 5 albums on Spotify and iTunes, and fluent in several languages. He has had ample coverage by national and international press and media, and is featured on Amazon Prime. He's a frequent keynote panel and tutorial speaker, and has received numerous awards. He's a top 1% cited innovator across all the science fields globally. He was professor in wireless communications at King's College London and director of the Center for Telecommunication Research from 2013 to 2021, driving cross-disciplinary research and innovation in technology, sciences, and arts. He is the co-founder and former CTO of IoT pioneering company World Sensing, co-founder and former CTO of the AI-driven satellite company SarasInsight.ai, and co-founder of the sustainable company Moving Beans. He also worked as a senior researcher at Orange France Telecom from 2025 to 2008. It is my honor and privilege to now invite Michel Doha to take the floor. Michel, the floor is yours.
Fantastic, thank you, Will. So let me just bring up my slides. I hope you can see them. I propose we take questions at the end. So, let's take it easy. I'm going to walk us through, and then I have enough time today to take any questions you would like to take. It's a fairly high-level talk, but we can also deep dive later on, very specifically, and on anything you want to know about, KPIs, architecture, protocols. We can take it as deep as you want, as broad as you want. I'll just give you a brush of how we currently see the ecosystem evolve, and I hope that proves useful. So I sit currently here in Silicon Valley, which is quite an exciting time, I have to say, because it feels a little bit like internet, the internet era, I think 20 years ago, 1998, so 25 years later, we're designing this new internet, right? So we gave it a name, we call it the metaverse, and we may not agree with what it really entails, but it is very clear that it cannot exist on its own. It requires a lot of tech constituents, such as 5G. 5G advanced, 6G XR, so XR meaning VR and AR, maybe a bit of MR, and we need other technologies such as blockchain and all that. So, I don't have enough time to talk about all of that. So I cut it down to a few talking points I'd like you to take you through, right? So let's start with that. And the very first thing is I'd like us to understand, why do we need 6G, right? So we are really on the road to 6G, but we've got a fantastic technology called, 5G, and soon we're going to have 5G advanced, and then we go in the 6G era. So I'd like us to understand, why do we need it and where are we at the moment? So, and to start with, it's always quite helpful if we look at what the terminology of metaverse really means. So at the moment, it is a very gamified terminology. So it's really about a game. So when we think metaverse, we think, Fortnite, Decentraland, if anybody is into that. So, but these are games essentially played by really advanced players, putting essentially their, maybe VR headset, being in the game, very immersed, etc. And the majority of the games we have today, they run what we call a Web 2.0 construct, so meaning it's a centralized server or a slightly distributed server infrastructure, which holds the game and can process the actual, controls of the players. And we may or we may not in the near future to transit into an era which we call Web 3.0 era, and this is all about, hosting your applications on a distributed ledger. And this is really interesting if you start thinking about ownership, if you start thinking about, who's really part of the ecosystem, because, Fortnite, just to go back to Web 2.0, Fortnite is owned by a company called Epic, okay? And Epic has fantastic products such as Unreal Engine, which I'm using, I'm a big fan of Unreal Engine. And they've, thrown out this fairly famous game. But if something happens to Epic and Epic, decides to close Fortnite, they can just kill it off overnight, right? There's little we can do about it because it is owned essentially by Fortnite, by Epic. In contrast, the Web 3.0, constructs, application as we call them, such as Decentraland or Sandbox I've shown here. They run on a distributed ledger, which is owned by, multiple tens of thousands, hundreds of thousands, millions of people. And switching it off is not that easy. So therefore, the notion of ownership, resilience, et cetera, actually becomes super interesting in the era of Web 3.0. I don't think we have yet reached, peak time. In fact, we're going through some very dark times now. We're talking about the winter in all things, crypto, NFTs, blockchain, and all that. But I think Web 3.0 will regroup, and we currently, our focus in Silicon Valley is on regenerative transformer AI, ChatGPT. You will have heard about this. So I think that gives enough time now for Web 3.0 to regroup. But anyway, coming back to what is really, if we just really fish out the most important traits of these games, and it's really that immersive thing. There's immersive, it's persistence, interactive, okay? And persistence means if you go back if you go back tomorrow to Fortnite, you will find essentially the gameplay, if you left an object there, it will still be there. So it's persistent, it's interactive because you're playing with a lot of players, and it can be hugely immersive. So therefore, when we talk about metaverse, it doesn't mean it's a gaming thing. It doesn't mean it's a meta in the sense of a Facebook construct. It is really that next generation internet, okay, which is that immersive, persistent, interactive internet. That's really what we're trying to build. And of course, gaming is kind of the starting point, but we think this is not the end game. So, and if we look at it further, are there any applications out there? Are there consumers actually interested in that metaverse, in that XR thing? Ericsson has a really interesting report coming out. I think once a year, I would say it's the consumer report. And, typically we would query thousands of consumers and ask them, how do you feel? What do you think is a really cool thing in terms of technology? And we would get these market insights from all around the world, which really worthwhile to read. And it's all for free. Just go on our website and you can read that, okay? So, and it turns out it actually is a huge demand. People want it, right? So there's a lot of stuff we will not do in an immersive environment or in the metaverse, if you were. But there's a lot of stuff we spend more and more time in, and we can imagine a world where we are not only gaming anymore, but we're using this, whether you're going shopping or you're navigating complex environments. So I've always said I'd love to have, some AR glasses which guide me through, I don't know, Costco, right? So for those who are in the United States, they know what I'm referring to. Shopping in Costco for me is a barrier which is very difficult to handle. So if I had AR glasses where, my wife just tells me what I need to buy and then it guides me there, and this is like, I would subscribe for this for a lot of money, actually. So here you go. So a lot of other stuff coming out. Music, we've done quite a lot of music, actually. Me personally, sporting has really taken off. And, in fact, the N-Real glasses, AR glasses you can buy currently with British Telecom in the United Kingdom. You can watch football there. This is great. We're starting to spend so much more time in these more immersive environments. So demand is there. And the question is now, where are we in terms of technology? And that's what I would like us to understand today, right? And we in AirSearch have done something last year, which was a surprise hit. And we built something which is that immersive, persistent, and very interactive construct. So you see that lady here is putting on her AR glasses. There's the other lady who's being volumetrically scanned by this volumetric scanner. And they're communicating with each other using a 5G network, and you put on the glasses. And I actually tried them. You see that fancy picture of myself here, these futuristic glasses. I tried them on, and it's spatially persistent. It's really interesting, right? So I have the person, it was actually Ezra who was in front of me, the lady, she was in front of me. And so I'd have Ezra in front of me, and then I would move my head, and Ezra wouldn't move with me. She's actually spatially anchored right in front of me. So therefore, the spatial anchoring makes it so much more intuitive, much more like we would perceive things in the real world. And of course, this year, I'm inviting anybody who comes to Mobile World Congress. It's happened in a month's time. We have a lot more surprises on the table. I can't talk about this, but if you're in Barcelona, let me know, and we can show that to you. So here you go, right? So we did our first baby steps for building this very immersive environment, and we learned a lot. We really learned a lot in terms of, hey, what do you need in terms of resolution? What works, what doesn't? We learned a lot in terms of data rates, jitter, latency, things we always talked about on papers for years already. Those among you have been part of the 5G, design circus, which happened, literally maybe 10 years ago. There's a lot of work which has happened in academia back then. We talked about this quite a lot before then. Industry took it more seriously and started building the systems. And so suddenly we see a lot of that, what's actually truly, happening in terms of requirements. So here we go. We believe in experimentation. It's hugely important. And the other thing we did is we did so much more. And these are just a few things I can publicly talk about. But this one here was celebrated a while back. It's the first time we managed to completely untether a VR headset, right? So normally VR would have power cable or communications cable, or it would run on Wi-Fi, and I'll come to this, but we kind of implemented a 5G constructor. We did this right in Silicon Valley, and we took AT&T Spectrum, we took AT&T's content, they owned Harry Potter at this point, we took Ericsson's 5G infrastructure, we took NVIDIA's edge cloud rendering devices, Cloud XR, we took Qualcomm's chips on the UE side, so on the headset side. Dreamscape actually built the content, and Weaver kind of rendered that. So we had a really sweet combination of partners here, where everybody concentrated on one part or another of the stack. And we were able to show that 5G can do that. So what happened is you put on your VR headset, and you go into a beautifully rendered, high-resolution world where you can experience Harry Potter. And you would move your head, and the world would be re-rendered. And in fact, the rendering didn't happen in the headset; it happened on the edge cloud, right? NVIDIA's Cloud XR. So we would use ultra-low latency 5G to communicate that the headset has shifted. Then the image would be re-rendered. It would be streamed down like a ultra-low latency Netflix movie, and you would be fully immersed, and you wouldn't even notice that all the computational heavyweight has been done in an edge cloud somewhere nearby, right? So, and this is now actually commercial product, right? So if you go, I tried that in LA again with Dreamscape. In fact, I think they've deployed it now in New York. I don't know exactly, but Dreamscape is it's fascinating. It's kind of the cinema of the future. You just go in like in a real cinema. They have this really beautiful entrance there. You get your tickets, and then there are up to, I think, 8 people who at the same time are allowed to go essentially into the experience room, and you can then experience different shows. And they're not overly long. They're 15 minutes to half an hour, if I remember well. But so immersive, it's just unbelievable. And, I became a big fan of that. So we showed for the first time, you can do it with 5G. Why is 5G interesting, you will say? Because you'll say, hey, we have it on Wi-Fi already. So the interesting thing is Wi-Fi collapses fairly quickly. So you can do day tours, actually. You can do 1 or 2, players really well. A cinema goes really well. But anything beyond that is a real stretch. So in 5G can handle that easily. You can have 10 people, 20 people at the very same time participate with one single access point. So that's the beauty of that, right? So and we wanted to show to the world that we can do that. So here you go. Dreamscape, just write it down. If you're in New York, if you're in Los Angeles, go and see them. But this is what we learned, right? So we kind of really learned that, hey, if you can do things along the devices. So as an example, if you tried the new Quest Pro from Meta, it's really an impressive design, even from a physics point of view. Really great resolution on that. We kind of learned, what are the limits of these devices where you do stuff on the actual device, right? Turns out that the 4K device, which currently you can get, the 4K VR devices, are very different to the 4K devices we have. For instance, I got a smartphone here, which is 4K, ultra high resolution on my smartphone. I really enjoy, I can zoom in on the photos, which my daughter sent me. It's just, I get this really kind of 2D, fully immersive type of experience. Now, once you go into the VR headset, you get, in a 4K headset, you get 2K here, 2K here, so 2K on each eye. And suddenly it is not anymore this amazing experience. So my personal, and this is really my personal kind of feel, is that we will not stay for very long on a 4K device, or on a 2K and 2K. We have to go at least onto a 4K and 4K, which becomes 8K, if not 12K or 24K. So I really think we need to do that, because otherwise the experience will be, suboptimal compared to what we get on the smartphone today. And how can we expect billions of consumers start going into a fully immersive XR experience if it's underwhelming, right? So therefore, we probably need higher resolution. Once you have higher resolution, well, to render this stuff is going to be very, very complicated. It's going to drain power like there's no tomorrow. You put on the headset, whether that is AR or VR, you have it on maybe for 10 minutes, and you probably need to recharge it, right? So therefore, how do we solve it? Well, the solution is to render everything on the edge and only consume power via the comms link, okay? So if you enable this, then you're on a winning streak there, because in terms of GPU power, you can throw it in what you want. You can go from 1 watt on the device to suddenly 350 watt to really powerful NVIDIA or, other GPUs. Memory becomes unlimited. Battery actually, becomes really, the battery consumption goes down significantly. In fact, our Ericsson research folks have measured this the other day, and they wrote a blog about it. If you're interested in, just connect with me on LinkedIn, and I'll find you that blog, where they could show that the power consumption has gone down by a factor of 7, and this was not even optimized. So imagine you optimize that, you get an order of magnitude power consumption improvement. Order of magnitude is a big deal. It means that your device can live, 10 times longer. If before it was an hour, now it's 10 hours. If before it cost $3,000, it will now be $300, or hybrid there, right? So therefore 10x is hugely important. And that's why, batteries get smaller, and it's a real value. The only bummer is connectivity, right? Because you need to move from an era where you do something like a few kilobytes per second to an era where suddenly you need not only, megabytes per second, but it needs to be what we call TCC, so time critical comms, because your packets need to arrive within a very, very low latency. And what we learned with a very low jitter as well, right? So because the rendering on the GPU cloud needs to learn exactly, needs to get the packet, the frames coming at exactly the right, tick, so they can do the rendering and stream it back down. If there's a jitter, right? So you just, the GPU is completely off from there. So the challenge now has turned from away from battery, away from GPU on the devices, away from the memory, to the comms network. And this is where 5G comes in, 5G plus, 5G advanced, and 6G, right? So this is really where we need to make that happen. So you will see in the first years, we will not have a lot of that edge cloud rendering stuff, but heed my words, remember my presentation in 2025, 26, 27, maybe at the end of this decade. And you will remember Misha told you, 4K, not enough, 8K, 12K, 24K, and we need to do edge cloud render. So let's see how this plays out. If I'm wrong, I owe you maybe a coffee or drink. So here you go. But this is how we see it at the moment. And that is really exciting vision, really, because everybody has now a role to play. So we understand now why we need to work towards 6G, because the amount of data rate which goes up and down is just mind-boggling. And you multiply by 1,000, meaning the 1,000 people in the cell, and you suddenly start to realize, hey, we have real bottlenecks in 5G. This is like the uplink rate above all, to be honest. Uplink gives us a lot of headaches. So if we find really good solutions for that, that's the way to go. So 6G kind of is natively jumping into that journey, that XR metaverse journey, which we have now ahead of us. So let's look at this a little bit more closely. And a lot of folks have started to look at use cases. We just said, you know what? We asked a simple question in Ericsson. So where do we want to be in 2030, right? So what do we want this network to support really from a society point of view? And we kind of came up with 3 classes of use cases, okay? And I have kind of constructed that for myself into these 3 classes. And the first one is like this immersive XR experiences. So you see the lady doing the shopping here, it's augmented overlay, it's an AR shopping experience. She may wear contact lenses. She may have an NFC chip which connects essentially to the billboard, which only she can see. So it's essentially, I see it from a comms point of view a little bit like 5G plus, okay? So you do it better with, you will do it better with 6G, but we could do it with 5G and 5G advanced. 6G will clearly help, but it will not be, indispensable in this sense. Use case number 2 is a different ballpark figure altogether, and we call that a holographic society. So you see that couple having dinner together, and it's, we're almost in Valentine's Day, a very romantic setting here, but they're actually physically not together. Okay, so they're physically apart. They're being projected into each other through these holographic, kind of projections. And if I hadn't shown you our own holographic holotaring applications a few slides earlier, you would have said, Misha, forget about this. This will never happen. But I have seen it with my own eyes, and this is 2022 when we did that, right? Imagine what we could do at the end of the decade. Now, to make that happen, a lot has to happen. In fact, I'll discuss quite a bit of the challenges we have ahead of us to make that holographic society use case really happen. The third one, in my personal opinion, is the most difficult one. And we call that the reprogrammable worlds use case. So suddenly comms plays a central role to sense, to really understand the environment, to communicate this quickly enough, reliably enough, and edge cloud does the processing, and then reprograms the worlds, right? So it does, in this case, it would, stop the bicycle of crossing the junction, or it would change the light of the traffic light, or it would reconfigure my room. I'm sitting in a room, I don't like the chairs, how they're laid out. I could imagine each of these chairs by the end of the decade having MEMS, build on the bottom of the chair, so they would just refold and, in the way how I like it, change the color of the room, etc. So we can start thinking in a very, very different way. And I think this is a hugely complex use case, not only from a technology point of view, but also from a regulatory point of view, from a privacy and ethics point of view. So there's a bigger ticket attached here. And that's why, for me, this is like the most difficult one to solve, right? Okay, so we have these 3 use cases, and we kind of, constructed that then into these bubbles of the specific 6G use cases. So we talked about the Internet of Senses, connected intelligent machines, programmable worlds, of course, make it all very sustainable. And we published a paper, which we, very early on, actually, we were one of the first ones to republish 2018-19, a 6G vision paper, which was which was updated in 2022. So there's an update now. You can download that for free. And we realized to make that happen, we need 4 big bubbles of technology, right? So the first one, the blue one, is all about connectivity. This is really central to our, is our bread and butter in a sense in the telecommunications world. Make it happen, more frequencies, better networks, make sure it's very reliable, works everywhere. The second thing we realized is that we really need to flatten, network and compute, and that's hugely important. Currently, as an application developer, you really have to worry where you're going to put your load, your application load, right? So, in this future 6G era, where we need to render a lot of things within 10 milliseconds of my consumers, you don't want to think about this anymore. So we really need to flatten entirely compute and networking. So this becomes all the same, and the loads can be virtualized. They can be moved around. And in the telco world, you have two loads actually. You have the telco load and you have the application load. So the telco load, specifically on the user plane, would be the UPF, the user plane function. You need to ramp this up as a possibly on demand. You need to then transit. You need to deal with your application load, etc. Hugely complicated. How do we make this happen? Can we API this? Can we build an API-centric network, right? Ericsson just spent a lot of money the other day, $6 billion to be precise, to buy one of the biggest API companies on the planet called Vonage. So we are serious about this. We are very serious about flattening network and compute because we think this will be a game changer. The third one, then, we realized is, wow, this is going to be very complex. So if you really build limitless connectivity and network compute fabric, you have like 1 billion data points to optimize every single millisecond, and no human can do that. So we need very native AI, this cognitive networking capabilities in there. And then we realized that, wow, we have a machine in there, right? So there's a machine now taking decisions, very critical decisions for us. Can we trust it? Is security good enough, right? So, and then we kind of realized that another really big bubble there are trustworthy systems, explainable AI, all that stuff, which in the research community we have been talking about for quite a while, is now going into production. It's coming closer to production. I personally think it's super exciting. Okay, very, very exciting. And those who know me, they know I worked at King's College for quite a few years. We have, back then, co-pioneered a lot of these fields actually. So trusted AI and explainable AI actually came out of King's College. We worked a lot on AI networks. So it's very exciting to see that now transit into a production environment, and that will be our 6G era. Of course, we're not the only ones, okay? We are by no means the only ones. Our friends in the early days, and competitors later on, the likes of, Nokia, etc., around the world. We have our clients, our supply chain. Everybody is starting to wonder, what are these 6G use cases really? And the good practice has been now for years to actually form alliances. These are industry alliances. They don't really, report to the government or to any of these standards bodies. They just start to build a coherent understanding on what that next generation should look like. And above all, why do we have it? Okay, so Atis here in the United States, has spent a significant amount of time, coming up with these use cases. And Ericsson, along with our partners, we do have some executive chair positions here and have massively contributed to this. And not only this one, there's an equivalent in Asia, in Japan specifically. European Union has just fired one out, I've seen today on LinkedIn in the morning. Then NGMN, I can really recommend you to read the NGMN report, because NGMN has not only looked at, what use cases we need and why we need 6G there, but they really try to separate very clearly what is 5G and what is 6G. We often forget about this, okay? But you really need to clearly separate that. And the reason is because the operators want to know, hey, what is new in for me? Why do you ask me to build a new infrastructure out there? Not long ago, you told me 5G is the best thing, which was produced ever since sliced bread, and now you tell me it's 6G. So we need to really give a coherent answer as a community why this is important. And as you have seen, as I've built a narrative for you now over the slides, it is important. If we believe in an immersive society, if we believe in an internet, which will be substantially more spatially aware, three-dimensional, we do need 6G, right? So you read the use cases here. I think, that's all obvious, but read these documents if you're interested. And if not, again, connect with me on LinkedIn and we can have sessions to go through. So anyway, so we have this. So what's happening now with these use cases? Well, these use cases are typically being translated to key performance indicators, okay? And this is a Misha slide. This is not an Ericsson slide. This is not an ITU slide. I just wanted to show you a few stats here. So the first thing we always observe is that no matter how hard we try for it not to happen, in the end of the day, as we go from generation G-1 to generation G, something always gets better by a factor of 10. Okay, so our peak rates, in the 4G era was around 1 gigabits per second. The 5G era is 10 of gigs. And therefore, by virtue of extrapolation, we expect this to be something like in the 100 gigs arena, right? So the same with the average experience data rate will probably go to 1 gigabit per second. We will have user plane latencies of a few microseconds. Energy consumption is going to go down by an order of magnitude. And we often, we don't know exactly why we need this. Not all use cases really require these type of KPIs. We also have no clue yet really how to do it. But it just turns out that every single generation, we didn't know how, we didn't know why. And yet when time came about, we needed it, okay? So therefore, these are numbers you will see in 2030. Okay, I bet it. Again, this is not an Ericsson bet. This is an ITU bet, but I think it will happen. But then I did something else actually. Quite an interesting thing I do with every generation. I've actually been involved ever since IS-95, working in COSAP these early days in 1996. I think I remember Gerd Fettweis. Gerd Fettweis brought me into the telco world anyway. So. I always multiply these numbers and I come up with these data volumes, right? So in 5G, we had 10 terabytes per second per square kilometer. And you can imagine, we have, if you go downtown New York, you can probably deal with these type of densities. Now 6G is going to be a different ballpark figure altogether. Suddenly, if you multiply everything together, you end up with 10 petabytes bits per second per square kilometer. Who needs 10 petabits per second per square? I have no clue. To be honest with you, even my creativity comes to an end there. But then suddenly I had an inspiration. I think these numbers make sense again when we stop thinking 2D, we start thinking 3D. Okay. And again, think end of this decade. And there's a lot of stuff happening in Silicon Valley in this corridor from South Bay Area, San Jose, Santa Clara, where I'm sitting, up to San Francisco. Drone companies, flying taxis, right? So imagine just 1% of the world, going from driving, Teslas to flying Teslas. Okay, I'm improvising here, as you can imagine, but just starting to think really three-dimensional. You suddenly you don't normalize anymore per square kilometer, but per cubic kilometer. Then suddenly these numbers will make sense, right? So I'll leave you with that a little bit of food for thought here on how this could potentially play out. So. Anyway, so it's the ITU who, interestingly, has to come up with these KPIs to then decide, hey, what is going to qualify as a 6G system? And they're on it. They haven't thrown this out yet, but they are on it. And the industry ecosystem now really has gone into gear, okay? And there are really two cycles you see. There's a blue cycle, which is the engineers, okay? And the green one, which is the ITU, which is more policy, techno-policy, okay? And they're very different, but they're very related. And we don't have a lot of time for these very first, action items to happen. So if you look at the blue timeline, those who are skilled in the arts, they know that, actually telecoms doesn't work in generations and works in releases, okay? So the engineers to really design this, they every 18 months, they throw out what is called a release. And that release has, tens of thousands of pages of specifications. And, it really ensures that the whole world is able to communicate. So today, as an example, my iPhone, I have an iPhone here, I can buy it in the US with a SIM card, maybe from, I'm making this up, right? So I'm buying the phone in the US, it's maybe produced somewhere else in the world. I get the SIM card from the UK. I'm traveling in South America. I'm calling my friends in Australia, got the phone in Asia with the SIM card from, from Central Africa. And it works, right? So it is actually kudos to this blue ecosystem that we get these systems working. It's a real success story. It's hugely complicated. This goes anyway. So the story is that we will really start seriously talking about 6G in release 20, which will start around mid-2025. We are now beginning 2023. Already in release 19, will be first requirements discussions. We got a year and a half, maybe 2 years to do a bit of magic there. So, and these are really the years where we are ramping up, R&D in the industry ramps up. We are looking more seriously what the academia has been cooking for the last 5 to 10 years. So it's a great time now to be in that field. And at the same time, the blue line cannot do anything unless the green, the ITU part, gets their act together. And the ITU really is responsible for getting more spectrum, for getting the requirements, etc. And the spectrum part, I've highlighted that in red actually, is only being discussed every 4 years. This is not something we discuss every day. So the 3GPP delegates, the blue guys there, they meet, every month and a half and sometimes a bit more often to discuss things. The ITU folks meet every 4 years, and that's the real bottleneck, because if we want spectrum for 6G, this needs to be decided at the World Radio Conference in 2027. We cannot decide anything in World Radio Conference in 2027 unless we table some action at the World Radio Conference 2023, which is at the end of this year in Dubai, I believe, or Abu Dhabi, I can't remember. So end of this year, November. Right, so it turns out that we really need to make the regulators around the world understand that we need more IMT spectrum, because otherwise we can't support neither the uplink nor the downlink for a fully immersive society, right? So I think we're good with Wi-Fi. Wi-Fi has a lot of spectrum. We just really need to get a little bit more for the IMT world. So it is a bottleneck at the moment. I don't want to lie to you. It's currently a bottleneck. If any of the regulators happens to be on the call, please get in touch with me. I'm sitting actually on the board of 2 regulators of the FCC, so the Technical Advisory Committee there, and of Ofcom, the Spectrum Advisory Board. We're working 24/7 to make sure there's a coherent story there. So I just want you to understand that it's hugely complex and 2 different worlds really there needing to synchronize. But at the end of the decade, I hope we're going to have it. We're going to have first implementable specifications by 2028. Then the whole machinery goes into, the Qualcomms of this world, the Apples of this world, the Ericssons, Nokias. They will start building the networks. And, at the end of this decade, hopefully we will have 6G. We'll see how this plays out, okay? So here you go. This is how we see that from our point of view, what it needs to include, really. Look, we played this triangle game for quite a few years now. Those who are skilled in the arts of telecoms, they know that in the 5G era, we talked about 3 very cryptic, application areas. The top one on the left is called EMBB. It stands for Enhanced Mobile Broadband. Think of just broadband, better Netflix. Okay, let me put it like this. Okay. Then we talked about on the bottom left, we talked about URLC, which stands for Ultra Reliable Low Latency Comms. Think of connecting very critical sensors and robots and make sure that the data which is being transmitted happens reliably and quickly, so that, let's say, your car doesn't do weird things or your robot, causes some damage. Then the bottom right one is called MMTC, which stands for Massive Machine Type Comms. Think of IoT at scale, connecting your city, connecting your farms and all that, right? So that's all good. 5G, I think we did it pretty well, actually, I have to say. Surprisingly, we got an engineering construct which could deal with better Netflix, connecting robots, and making, connecting your cities, right? So we made it possible. And then 5G Advanced, which is now these 2 releases, release 18 and 19, we're going to expand that. We make it better, right? So EMBB++, et cetera, et cetera. But as we move in the 6G era, we're going to push the envelope again of these 3 vertices, but we're going to introduce 3 more vertices, okay? And you can see that we really think that AI and computing should be natively built into our 6G system, okay? It cannot be an afterthought. It cannot be something we just add on in the end through some form of orchestration. It needs to be natively in 6G. We need to make sure it supports immersive comms, and we need to make sure that to do that immersive comms, we really want this spatial temporal capability. So, you know, in the academic circles, we've been talking now for years of this joint sensing and communications, really the ability for my phone to communicate and at the same time understand what this room looks like, build volumetric clouds, trying to understand really, you know, what else from an immersive point of view could be delivered. Building this natively into 6G is an exciting roadmap, you know, loads of challenges, but if we get that right, you know, that would probably the very first comms infrastructure, which natively kind of integrates these very, very advanced, you know, communication concepts, right? And it's not the first time that telecom would do that. SDN, I think, you know, is probably much more, you know, predominantly deployed in the telco infrastructure compared, let's say, to the cloud infrastructure. I have no data here, but it's just my feel. Okay, so I think telecom is doing. It's very slow on some things. It's very, you know, frustrating that we always need to wait, you know, 10 years for a new generation. In fact, even a bit frustrating that we always need to talk about a generation. But you know, in the end, you know, that engineering construct, the blue cycles I'd shown you on the earlier slide, it's so solid that in the end, stuff is being delivered, it's being deployed, and it's global. You know that, I know that. If I take a plane from San Francisco to Barcelona, it will work. Okay, so therefore that's our 6G vision. From you know, we can deep dive if you have any questions. We can talk about this in many more details. But what I thought I'll do, maybe the last minutes before we go into Q&A, is really talk a few challenges here, right? So a few challenges. There happen to be 6 challenges because we're in the 6G era. So in the 7G era, you will have more from me, but for the time being, let's stick with 6. It could have been 100. I just picked those which I thought are like my personal top ones. And number one is really, you know, if we are serious about an end of decade cyber physical continuum, meaning where we're doing sensing, processing, and actuation at the same time, we need to get more serious about a lot of things, right? So there's a lot of data being processed, a lot of data going up and down. Some of that is super critical, super critical, right? So the question is, if I lost a single packet over the air, you know, could that cost lives? We don't want that, right? So it's something where we want to really ensure there's a stability there. We want to make sure that machines don't take over, that there's a weird thing happening because of some async of some control loops. So therefore, the ability to observe, act, and you know, to predict stuff, super important. Which is why our community is really driving this notion of digital twins as part of that envelope. Because you know, in digital twinning, you can then take your network, you can take your real world, you can take your robots, you can take your decision makers, bring it into this simulated world, and you can start building, you know, very sophisticated scenarios. AI can learn natively before you put it into the wild. So one of the biggest challenges, and very few people talk about this, interestingly, you know, I feel it's more NVIDIA talking about this in the computing world than actually our telco folks. So if anybody in telecoms is on this call, you know, I beg you, we need more of these skills in our realm of telecommunications. Number 2, it's really the spectrum trap, right? So we fell a little bit into the spectrum trap with 5G. In 5G, we talked a lot about millimeter wave, and you know, there's a lot of excitement around the millimeter wave. Not surprising, there was a lot of excitement, above all among you know, academics, because you could publish a lot, would probably get a lot of citations, and you know, it's I think a fantastic thought leader experiment to go with that millimeter wave thing. But you know, looking at the deployments now, it's simply because of the, you know, economic aspect of that whole thing. It is not even within 1% of what currently 5G constitutes, right? So, and that's pretty sad, because we have actually spent billions of dollars, not only the government funders, but also the industry actually spent billions of dollars and tried to make that millimeter wave work. And I think it will come eventually, right? So I'm not saying it was a bad idea, but it's just we need to get our priorities right. And priority in the end of the day is where we can really enable these advanced 6G use cases, where we can get it lapsed, we can get the coverage, we can get the data rate. And it turns out that, some sweet spots which are still available is between the 10 gig, the 7 gig, actually 7 gig to 15 gig, right? So you see that green one there. It's really essential. We really need that. That's really where we want our 6G systems to sit, okay? And then we do got the complementary stuff, like millimeter wave today is complementary to our mid bands. We want that sub-terahertz range to be complementary to our essential centimetric range, right? So, and that's really what we need to drive. And why am I always saying that? I'm saying that if we really want joint comms and sensing, as an example, if you're an academic, please not only give us a solution in the sub-terahertz range, it's the easy range. We know that the wavelength is very short, you get superb resolution, and that's all good, but it really, if you want this to be a massive impact by the end of the decade, this has to work in the essential centimeter range, right? Can we do other things there? And that's why we have, smart engineers, smart academics to come up with that. So focus on that. Let's not fall in trap and do the easy thing. Let's do the difficult thing, but the thing which will have a lot of, gravitas towards the end of this decade. So therefore, I'll leave you with that. And I'm hoping to see some solutions soon. What else? AI, right? So we talk about AI. I've been probably exposed to AI in telecoms ever since I was in France Telecom in Orange between 2000 and when was that? That was 20 years ago, 2005 to 2008. And, Release 8 just came out and we talked about self-organizing networks and all that. So this is where we first time talked about this. But if you paid attention, we've really used back then, AI to configure our networks. And it's only now that we're starting to make this happen, okay? If you look at the world of SMOs and RAPs and all that, where AI is really helping us to configure networks, take very quick decisions. There's a lot of AI in our networks these days. So we just released, I think, 200 new AI products the other day. It's really now taking exponential pace. But what we are really doing is, we have humans design the networks and AI configure that, right? So in 6G, I think AI will be much more native as part of the whole telco offering. There's no other way. We cannot build it as a posteriorly thought little thing where we say, okay, 3GPP, tell us, give us a black box where we can put AI so it can do a little bit of magic, a bit like the NWDAF function in the core network these days. It needs to be more natively built in, right? So that's really what we need. And we're working on that. And I think that will be super exciting. This is really where telecoms and computer science really comes together, because if you look at how generative AI, transformer models and all that have changed the landscape within weeks, I'm not sure if you guys see this, but there's this new stuff coming out every single week. It seems like AI is optimizing itself, becoming this era of singularity, but it's going out exponential speed. So, and the telecom will not be spared, and 6G will be a native fertile ground for that. Then the fourth one is all about energy. And I really think, just looking at how the industry ticks at the moment, how Ericsson ticks, how our industry partners globally tick, I think energy will be one of the battlegrounds. Okay, in 5G, 5G was really how many gigabits per second can I pump through the network? This time energy will be more serious. And so we're looking at trying to understand, could a future in 2030 look like a zero energy device future? Meaning, IoT devices probably could be running completely off battery. But hey, can I push this a bit further and say, could my smartphone work actually at zero energy in average, or at close to zero energy? So and then can we push the envelope further? Can we build networks which are carbon neutral? So they may use a lot of energy at some point, but get a lot of energy back at some other point. If that's the case, what's the impact on the architecture? What's the impact on the protocols? This stuff has to work. You can't just disconnect an ambulance because the network doesn't have enough energy to actually power my base station or my user equipment. So I think these are very interesting challenges, and a lot of academic research has been done over the last 10 years. And so the magic will be now to translate that into operational systems. And heed my words, energy will be one of the important battlegrounds in the 6G era. And another one, which I find very exciting, is for our industry to get away from this ARPU model. So ARPU stands for the average return per unit, I think. In essence, it says, the operators are being paid by the number of SIM cards sold, okay? We've tried for many, many years to transit from an ARPU native business construct to a service industry to make money the same way as Google or Meta or Apple would make money, but we have failed. Okay, and then suddenly it struck me, maybe we could actually learn something from the Web 3.0 construct. So look at this chart. It looks very complicated, but I'll talk you through. So we see the dotted black, the dotted forks in the black lines here. This is our traditional infrastructure providers. And apologies if you don't see your logo there. I didn't mean to omit it, but I just said limited space here. So I have completely randomly chosen. So this is like the traditional stack you have. So if you now want to play a Fortnite game, Epic would write Fortnite based on that traditional platforms and connectivity and device and components. Fortnite turned out to be a hit. So then Epic thought, hey, how can I monetize that? So then they introduced, paying options for PayPal or Visa or MasterCard, etc. So essentially, a monetization is being built in posteriorly rather than thinking up front. Now, the Web 3.0 community has actually taken a very different stance on this. So look at this. There's a new platform there, which is our blockchain platform, right? So you have a blockchain, could be Ethereum, Cardano, or EOS or Solana, whatever that is, right? So it's a blockchain which runs on the traditional stack there. So this, I'm talking about the green box now here. And before you can write any application on this blockchain, you need another layer. And I call that the value layer. Okay, so you need tokens, you need wallets, you need exchanges, you need NFT markets, etc., marketplaces, assets, and all that. Right. So you have constructs like a token called Sand, as an example, which runs on Ethereum. Right, runs on a specific ERC Ethereum contract. You have MetaMask, so the Web 3.0 aficionados on the call will know what I'm talking about. MetaMask is your wallet. Coinbase is where you exchange, is an exchange, etc. Now, the only then, once you have that value layer, can you put the application on top, right? So Decentraland, as an example, or Sandbox or Upland, and actually, by the way, I think Upland is just neighbors of us here in Silicon Valley. I thought I'd seen the CEO of Upland having lunch here the other day. So, these folks, Sandbox as an example, cannot run without the Sand token, which cannot run without the Ethereum blockchain, cannot run without all the other magic we've been traditionally doing. But the interesting thing is, if any value is being created in Sandbox, either through activity or through sales or for asset trading, the value goes up. Value is being natively generated. Nobody had to think of building a payment option posteriorly into the construct. It was there from day zero. So my postulate is that, if we borrow some of these concepts into the telco world, listen, we have a good chance of getting away from this ARPU monetization model, right? So I'll leave it at that. I'll let you think about it. My last, challenge, and that's really about privacy. Privacy is a big bugger, actually. I think our engineering community is pretty solid in security. We build really good secure systems, right? If you look at the stack, in fact, you got security at physical layer, at medium access control, at networking layer, all the way up to application stacks. So in fact, you do like 7x encryption of your data packets. So security is pretty cool. Privacy is not cool. So, if you want to use a specific app, you need to tick off the T's and C's, the terms and conditions of the company who's providing the application. And if you like the application, even if you dislike the T's and C's, you will use it. Okay, you will use it. It's secure, but you don't know what's happening with your data once the application providers actually decrypt that, right? And this is, I think, where our community could play a bigger role and just say, hey, we see a lot of the contextual circumstances where that data is being generated or consumed. Can we do more about this? So just think about my AR glasses. So my AR glasses see the world, okay? And maybe the people it sees do not want to be identified. And are there things we could do, using AI and some other smart things like natively build privacy into our telco stack? And I think this is maybe one of the most important things we need to get right. How we can support that. This will support the regulators. I think it will support a lot of the ethics discussions. To the point where we feel comfortable where I feel comfortable having, my daughters spending time in this new fully immersive 3D internet. Okay, so I'll leave you with these 6 challenges, and I hope I gave you a nice narrative of where we are going. Things are happening. Sometimes we get bumps, right? So things not always work out as we think, but the trend is there. And we need 6G, 5G Advanced 6G to really make sure this works out. And then we need to solve on the way all these challenges. I'll leave you with that. I'm very happy to take any questions. I'm happy to share the slides, by the way, as well. So I put some references in there. It's a nice blog we wrote, and loads of other blogs, actually. So a lot about XR and metaverse and 6G. Read up on this, connect with me on LinkedIn, and I'm going to stop sharing. Which just if there's time for question, Ashutosh, and I don't know, I'm happy to take these. Thank you.
Can you describe the requirements for the stereo camera and 3D display that is used?
So this is presumably with respect to the holotaring we did. So we used actually glasses which are commercially available. The company is called Nreal, and you can buy them commercially now, actually. In the UK at least, I know you can do that, and probably globally as well. It's a pretty decent graphics, but new stuff is coming. So, if you have a bit of patience, Mobile World Congress, I think will be really pivotal now to tell us, how this ecosystem will play out. The announcement of the big players, such as Meta, Apple, Google, Samsung, in this space will really move the market, I think, over the next 12, 24 months to come. So that's on the display. I think at the moment, everything is 4K. So I think it's 2K and 2K really. So I don't think there will be massive changes. The change in my personal views, and I haven't seen actually the roadmap, but my personal views, we need to work a lot on the optics to get this really fully immersive. It will take a while. But next 12 to 24 months, a lot will happen. Yeah, thank you.
All right, next question.
Question for the floor. You mentioned about the KPIs that you are pushing through the ITU. Mm-hmm. Have you done any kind of simulation to determine when the choke point will occur on the networks? Yes, we have. Is a good question, and I have several times you heard me alluding in big pain about the uplink. Okay, so the uplink is a real bottleneck, has always been. So this is not surprising. It's simply imagine, a cell user at the very edge or deep in the basement needs to communicate with a target cell, and then ends up essentially causing a lot of interference with other cells. So uplink is a real bummer, and we have done, capacity analysis, and, we still have a few years to go. We should be fine. But at some point, the crunch point comes in, and meaning then we have a choice, right? So either we accept we will not have a fully immersive society, okay, which is go flat with watching Netflix movies, and or we need to densify. And it's a big take for the operators. Remember, operators are being taxed actually twice, upfront where they pay for spectrum and posteriorly when they make money. Okay, so therefore this is a big ask to the operators to say you need to increase the density of your network by 10x. Is a lot to ask, or we get more spectrum, right? So therefore a balance of these, and then of course having better equipment. So there's really a lot of magic happening in terms of very specific 6G technologies. I haven't talked about this at all today. Ashutosh, feel free to invite me again for another talk where we specifically talk about 6G technologies. So 6G technologies, denser networks, more spectrum, or not doing anything at all. So therefore, these are the trade-offs we need to do, and we need to start thinking now so we can address that crunch, which will come in a few years' time. Thank you.
Next question. Are there requirements on end user devices that have to meet future metaverse use cases, or is all of the advances needed in networking?
That's a great question too. So, what I'm not sure you've been wearing any of these headsets, but some of them get quite warm. There's a lot of processing happening. So it reminded me a little bit of the very first 3G phones. You remember, you could wear them, you can carry them around in the winter, and it was actually quite a good design. But we don't want this. So there's a lot of work now on the device manufacturers, and actually, to be honest with you, a lot of kudos to Qualcomm, who has been driving a lot with their Snapdragon 2 and their Spaces program. Just look it up. It is really a market maker. They're providing a lot of reference designs so companies can trial around, they can play around, they can understand whether it would work with the network. But a lot more has to happen. Really, a lot more has to happen. Particularly, what we are very keen on is having, my future AR glasses natively 5G connected. Okay, a bit like the Apple Watch. Okay, at the beginning it was tethered to the iPhone, and only lately became actually totally untethered for a separate eSIM. Now we want the same for the glasses, and this is a tough cookie. Let's see if Qualcomm manages that, but it's difficult. So yeah, they have homework to do.
With the 6G, as we go into smaller cells and a lot more number of cells, do we expect the operator to invest in backhaul, fiber optic, and all this extra capacity going to be needed, or we envision government, or because that's going to be a huge investment? I can foresee that.
Yeah. So it's a good question. I don't have, I'm in the US now for about a year, so I don't have the full visibility here, but I can tell you, like in the UK, as an example, there's a lot of discussion of actually trying to understand where could government come in versus private investment. And, of course, governments need to be very careful so this does not become a state aid, which would then violate a lot of the World Trade Organization rules. And but I think it was generally agreed that the government plays a big role. In the US, in fact, there's a program called the BEADS program, which is a multi-billion-dollar program to roll out fiber and all that. So I think the big backbones, they will probably need to be subsidized in one way or another to make that happen. But then the edges should really be privately owned. And my personal view is, again, this is my very personal view, I'm not representing here the regulator nor Ericsson, is that if you look at it, the telco operators did not have it easy. Okay, they're being taxed twice. There are very few industries which are being taxed twice. And we probably need to think about new models so the operators could start thinking on reinvesting that money they make rather than paying the treasury on the spectrum auction. They could maybe use that to densify some of the investment, right? So that's just this is Misha personal thinking here, but we need to find a good trade-off. And that's why that's why that transition from ARPU to a non-ARPU API-centric type of business model is so important. And that's why that's why we bought Vonage for $6 billion, right? Because we think that transition has to happen. Otherwise, the telco ecosystem will not be sustainable from a growth point of view. From maintenance, always good, but not growth. So yeah, I hope I answered your question. Thank you, Samuel.
Yes, it does. And I agree with you. I also have background in the area, and I think has to be a win-win for everyone. Otherwise, it's not going to work.
Yeah. Thanks.
Next question. What are the most severe security issues for these use cases examples? Are they being looked at now for security by design?
Yeah, so security is a hugely important topic, not least because of a lot of black swan events on the horizon, right? So let me start with the obvious one, which everybody looks at, and that is quantum. I talk to security folks, and they maintain, quantum computers are a long way off until they can crack things. But those who are on the field, they know that our friends in China published a paper the other day, which wasn't peer reviewed, so we don't know really where it is. They claimed they were able to crack the very first, cryptographic keys, and that's worrying. If we can do this today, even if it's just, nominally, imagine a small breakthrough on the quantum side. And I'm seeing a lot of things here in Silicon Valley where I have to tell you this will come now much quicker than you think, so much quicker. So therefore, NIST had accelerated the post-quantum security requirements, meaning coming up with new ciphers, digital ciphers. These are not quantum ciphers, but digital ciphers which are able to withstand quantum attacks, okay? And the candidates are lattice codes. In fact, I worked a lot in that at King's College as well. So, but that's a whole era we need to implement very quickly because it will be the weakest link. So you can't have a beautifully end-to-end lattice encoded encrypted system. There's one link which has not upgraded and quantum threat could actually break that. So, and I think we're closer than we think. So it's not going to happen next year, but, watch out. So that's the obvious one. And then there's a lot of stuff, guys, which I think we didn't really pay attention to. And that is, simple things like, how do you provide root authority for, let's say, a virtual machine or a Kubernetes cluster you're ramping up, right? So it turns out a lot of these CAs, so the root authority, the certificates, which are being provided, are chained through many chains. So one certificate, says this one is valid, this one is valid, this one is valid. A chain maybe of 7 to 10 hops, and then you start, encrypting and authenticating your Kubernetes cluster, and you think it's super secure, but nobody actually bothered to check down what is the root authority. So I call that 360 security. This is not an Ericsson term, but personally I call it 360 security. So it's not only about making sure you encrypt everything properly from your UE to the GNB to the CUs of EUs up to the internet, but also, top down, the applications, the virtual infrastructure, even the managers. So think ORAN, if we introduce now SMOs and the O1 and O2 interface starting to talk to through the management plane, you need to encrypt everything. You need to make sure that everything works, because if one of these authorities is really not kosher, then you have a problem. So I think these are kind of the low-hanging problems we need to address. The ciphers themselves, if you exclude quantum and you exclude the root authority issue, I think they're pretty good, actually. So we're good on this end. There's a lot of stuff in terms of the metaverse, in terms of security there. Shall we use an extra set of security in the digital internet, et cetera, et cetera, et cetera. So probably I can talk maybe another day about this. It's a huge list of stuff, but yeah. Thanks for the question. Great question.
Yeah, I have a question myself. I know you have done a lot of theoretical work. You've also built systems. But in order to make something successful, you need to have some kind of a test bed, right? You get some interesting use cases. Can you say a few things about what kind of test beds should be building, or maybe some of the test beds are already there? For example, NSF power test bed, just to pick something, or 5G lab in Germany. Just your thoughts on that, how to accelerate the actual deployment of 6G.
Yes, is a great question. And, the experimental validation really gives you a lot of proof points very quickly. You learn very quickly what works and what doesn't work, and where the true pain points, which we need to be addressed. Look, I'm a big fan of national type of labs, which are sponsored by government. So the NSF would be an interesting kind of powerhouse to do that. And we have been trying to get this done in the UK for quite a long time, right? And I think the problem is that the academia, which typically gets the government funding, and the industry, who then deploys the system, speak a very different lingo, okay? And one big step we need to do, Ashutosh, in the 6G era is to align the lingo a little bit, okay? And it's really both parties need to play the game, and I'm serious about this, right? So the likes of Ericsson need to start speaking a little bit more, for experimental purposes, maybe not for market purposes, but for experimental purposes, needs to start speaking more, open source community type of stuff, or AI, what's being used in power. And really try to understand how this could be plugged into, semi-commercial networks. But at the same time, I think academics are not off the hook. They really need to understand, how does 3GPP tick? If I tell you NWDAF, you need to know what it is. You need to know how it plugs in. You need to know how it would actually communicate from an eastbound API into an RAP, which talks to an SMO and then speaks to the RAN. You need to know these things. So therefore, my request, my wish is, start beefing as academics and students. Start beefing up seriously in the industry lingo. And I'm your Trojan horse now in the in the industry world. And we will try to approach you halfway. So I think this may work, Ashutosh. Let's see.
What might be done for human-to-human communication without perception of delay?
So the industry has this great question. So the 10 milliseconds always come up again and again. And in the end, it's a hugely complex equation, what really determines the latency requirements. So if we were very, very strict, we would need to execute latencies between frames. Okay, so your FPS, your frames per second, really dictates you how quickly needs to be a round trip time, a full stop. Okay, so a typical Hollywood film would be 24 FPS, so very slow. You know, you have a lot of milliseconds to deal with that problem, but it's very blurry. So if you go to Netflix and you stop at any moment the film, it's always blurry. It's kind of something we adopted for the cinematic industry. We've never gone away from that. As you go into the fully immersive world, if you put on a VR headset, if you're at 24 FPS, you get completely dizzy. So the minimum you need to do is 60 FPS, and the industry currently is at 90 FPS. So if you buy a Quest Pro, you would be at 90 FPS. You do the maths, 1/90 is about, guys, verify this, I think something like 11 milliseconds. In theory, you need to have an 11 millisecond round trip time. So meaning I'm transmitting my movement of the head, re-rendering of the frame coming down. Now, 11 milliseconds round trip time is impossible. You can't do that, right? And then industry now talks about 120 FPS, which is 8 milliseconds. So therefore, the tricks which are being used is what we call, as an example, time wrapping or foveation. So foveation is using that fact that you are essentially never really looking at the whole field of view. You're just actually looking at a central point. So rather than re-rendering the whole frame, you just do a smaller part. So you gain quite a bit of bandwidth and bandwidth then. And the time wrap, which is being used, is that if the signal from the rendering doesn't come back quickly enough, you would do a superposition, linear or non-linear, of the previous frame, right? So unless you're doing ultra competitive, esports type of through your VR goggles, we are good. We can do that. So the combination of time wrap, foveation, and all the other tricks the industry has, we end up essentially with an end-to-end solution, which is quite solid. But that also means, we need new codecs, we need new standards, because what you really want is an Ericsson 5G network talking to an iPhone, but then also the applications, meaning the NVIDIA Cloudex are working with whatever a Meta headset, right? So therefore, we need new standard, new volumetric standards, which actually incorporate all these very advanced techniques. So I hope that answered your question, but that's a brilliant question. Thank you.
All right, so we'll have our last question. We decided on this one. I guess if there was one governmental or international policy, what do you foresee is needed to realize the 6G enabled metaverse? What would that be?
Yeah, so it's a difficult one. So again, I'm speaking as Misha here, okay? So please don't construe this as somebody speaking as part of the regulatory boards, nor of Ericsson. I think we need to work much more on net neutrality. And it's really one way for the operators to reap some of their double taxation and reinvest more in the network. So, the consumers don't have a frustration there. But net neutrality, of course, guarantees that everybody has the same access to networks, which we want. So we don't want to kill this as an industry at all, quite the opposite. But we need to think about new business models for the operators to leverage on. So maybe there's a middle ground. Maybe there's a way of saying, hey, let's have 80% net neutral traffic and 20% traffic which the operators can actually monetize on directly by fast tracking some of the applications. I think this needs to be sandboxed. It needs to be trialed. And, it might be a flop. It may not work. But if it does work, I think that would make a huge, huge difference. So I think that would be a nice thing to look at from a sandbox environment, So, yeah. And of course, more spectrum. And of course, ethics and privacy. But hey, the net neutrality is kind of keeping me up at the moment. So, yeah. All right. Thank you.
So the next talk is as a complementary to Misha's talk. And I have the pleasure of introducing Dr. Kumar Bijay Mishra. He's local, and this talk he'll be giving in person from this location. He works for U.S. Army Research Lab in Adelphi, Maryland. Dr. Mishra's talk will be dual blind deconvolution perspective of integrated sensing and communication. So let me just briefly introduce. He is a real scholar. He works for Army Research Lab, and he obtained his PhD in electrical engineering and MS in mathematics from University of Iowa in 2015. He also MS in electrical engineering from Colorado State University. At that time, he was also working with NASA's global mission ground validation. He got his BTech from National Institute for Technology, Hamidpur, as a distinguished, I think, he's a gold medal winner. He has been a prolific IEEE volunteer as well. I personally know him because he's involved in IEEE Future Network Initiative in the Massive MIMO working group. He's a distinguished lecturer for IEEE Communication Society, Aerospace, Electronic System Society, also IEEE Future Network Initiative. He has won many best paper awards. Can see that. He's been also elected member of 3 technical committees, IEEE SPS, SPCOM, and SPS. He has been also associate editor of many IEEE transaction aerospace electronic system. He got outstanding editor recognition award there. He has 3 books coming up, I guess. How do you get time to write 3 books? So you can hopefully can see those available pretty soon. Signal processing for joint radar communication, IEEE Wiley, next generation cognitive radar systems. And the other one is advances in weather radar volumes. So with that, I'd like to invite Dr. Kumar B. Mishra to take the stage. Thank you. So Mitch, you can, yeah. Right.
Okay, hello. Okay, good morning, good afternoon, good evening to all the people joining virtually, and good evening to everyone present here. Thank you very much to the ACM Baltimore Chapter and Ashutosh for the invitation to present this recent research we have been doing at ARL. So I'm glad that Misha spoke before me, because he gave an excellent overview of some of the concepts that I'm going to cover in my talk. So he talked about the spectrum trap and the need for academicians and researchers to get into this solving the spectral congestion problem. Also, one of his slides was about use cases of 6G, and one of the use cases was distributed sensing and communications, which is exactly what I'm going to talk about now. He also spoke about need for higher data rates, bandwidth. So all of that actually very nicely connects to this talk, where I'm going to first give an overview of integrated sensing and communications and what it is all about, what is the current state of the art. And then we are going to look into this problem called dual blind deconvolution that we have been working on for previous year or so. And then we'll look into some other emerging trends in this technology. So I would like to acknowledge Dr. Brian Sedler, Professor Arguello, and his students, Edwin, Roman, and Jonathan, with whom I've been working on this problem, as well as funding from ARL and the National Academies of Sciences, Engineering, and Medicine. And since I'm speaking at APL, I could not have left out references to spectrum, radar, and communications from some of my favorite sci-fi, space-based TV shows and movies. So you will see some references which are pertinent to this talk in some of my slides. So for example, here from this Apple TV show For All Mankind, they have a scene here which is talking about interference from radiation to the Earth-based communication systems. And I'm going to talk about interference from radar to communications, communications to radar. So obviously, interference to communications and radar is not a new problem. It has been around for a while. In fact, some of the very early spectral coexistence papers can be traced back to as early as about 1960s. And then only recently it is becoming more difficult because of new applications. Otherwise, conventional radar systems or communication systems have dealt with interference at the receiver in one way or the other for decades. So currently, I would mention two most important applications that are driving research in integrated sensing and communication. So one of them is obviously trends in wireless communications. As you can see from a graphic here, it is expected that in the future, we would have billions of devices that would be connected. And as a result, the data traffic would also increase dramatically. There would be need to store and transmit exabytes of data in the near future. So with this increasing demand in this high quality wireless services, like Misha mentioned, URLLC and several other applications, metaverse, we need a system to support these high data rates. So how do we do that? So we look into Shannon's capacity formula for some inspiration. And as you can see, this famous formula here, capacity is a function of the number of orthogonal resources n, which could be number of antennas or any other resources, maybe time slots and so on, bandwidth W, and then signal to interference plus noise ratio. So since SINR has a logarithmic relationship, you'll have to increase it a lot to gain this capacity. And then, yes, we do work with N, which is the number of orthogonal non-interfering resources. For example, you could adopt MIMO technology to increase the capacity. So number of antennas could be increased. But here specifically, we're concerned about the bandwidth W. Can we increase W? Now, obviously, it's a natural resource which is very scarcely available, and a lot of regulations exist on which bandwidth could be used for communications and radar. So there are already regulations there. And then it's not like spectrum is available and you can transmit everywhere. There are certain regions or frequencies in the spectrum where there is very high attenuation. So for example, in millimeter wave or sub-terahertz or low terahertz part region of the spectrum. And we, in that case, we have to exclude those high attenuation regions and focus only into transmitting within the atmospheric windows, which are regions of local minima in those regions of spectrum. So it is scarce. There are regulations. Not everything is useful. So we have to use bandwidth judiciously. And again, here is a connection with Misha's talk, because this lower graphic that you see here is what he had shown about for the future radio access. We could probably go to sub-terahertz. So this from Ericsson. So even though we would like to move to this higher end of the spectrum, millimeter wave or terahertz, it is still not sufficient to actually allocate spectrum for radar and communications, or radar or sensing applications and communications exclusively. Because the more we could utilize this, better we could serve the needs for wireless communications, that is high data rates for these various futuristic services. And radar's performance is also related with wider bandwidth, because wider the bandwidth, better is the resolution of radar, resolution being the capability of radar to discriminate between two very closely spaced targets. So radar also needs high bandwidth, but currently one of the applications that is driving the research in integrated sensing and communications, or ISAC, we sometimes also call it joint radar communications or JRCN. There are many different terms that, as we'll see in a bit. In radar, it's autonomous vehicles, which are the use cases which are currently being investigated, where we definitely need some way to share the spectrum between communications and radar modalities. So So if you look into some of the sensor-driven modern vehicles, where in some sense autonomy has been included in the system, then these vehicles, they typically consist, they have several sensors deployed on them. There's a GPS, LiDAR, cameras, ultrasonic sensors, radar, and so on. And these sensors are not just used to guide the vehicle in a congested traffic environment, but also to monitor the overall health of the car, for example, tire pressure and metrics like that, as well as to monitor the physiological behavior of the driver and passengers as well. For example, there are these in-cabin radars which could measure the heart rate or respiratory rate or even drowsiness of the driver, which could be very helpful. And if we look into what are some primary sensors, then there is a high resolution camera, which can provide a very good visual of the surroundings, and it also has semantic information. There is a lot of metadata that could be useful. However, it doesn't perform very well when there's low visibility, either because of weather or because of poor lighting conditions, and it does not directly measure the Doppler velocity. It could infer the Doppler velocity of the vehicles by looking at the change within the frames, but there is no direct Doppler measurement. Then we have LiDAR, which has been a favorite of autonomous vehicle industry for a while, because it provides a very high range resolution, but it is expensive and it is usually mounted outside of the car frame. So for aesthetic reasons, some vendors may not prefer that. And it, as I said, it has a very high cost, but currently most of the industry statistics are such that they do not want these kind of sensors to cost more than $100 in mass production. So LiDAR is very expensive. So we come to radar, which is a cheap sensor. It can fit into that $100 bill in mass production. And it measures Doppler velocity directly because it's based on Doppler principle. There is no semantic information like camera, but it is very robust to low visibility conditions because radar works both night and day. And in some cases, it can, even in a harsh weather, it can actually look beyond a distance that a camera would be able to visualize. So radar is important, and its performance, as I mentioned earlier, is directly linked to the bandwidth. The higher the bandwidth, a better resolution it can provide. Apart from this, a lot of modern cars, they are software managed, as you can see from another graphic from the industry that I've taken here. There are many functions because these radars are sometimes, the cars, they are sometimes fitted with very high processors. They're almost like a computer where a number of functions are monitored and managed through software. And they may also be connected. A car may be able to communicate with on-road infrastructure or with other vehicles, or even may have a satellite connection. So because of all these functionalities, these connected cars in the future as well, they are expected to generate huge data. And if we look into some of the industry statistics, it appears that current wireless technologies such as DSRC or CV2X, they are unable to support the kind of data rates that are expected from these futuristic autonomous vehicles. So, and as I mentioned earlier, to support these data rates, again, we need higher bandwidth. So these autonomous vehicles, they need higher bandwidth for both functionalities to stay connected for communications with infrastructure, other vehicles, or even some other, for example, base stations that may be dedicated for these purposes, and also to sense very accurately and give a good picture of the environment. So we need high bandwidth for all of these, and as we know, bandwidth is scarce. So shown here is a table of different IEEE radar bands, which are kind of already allocated for different applications. And as I mentioned earlier, the problem of interference or sharing of spectrum between communications and radar, that is not new. There has been some work in 1960s and even in 1970s, but it was really in 1980s when some of these radars which operate in VHF and UHF band, they started facing interference from TV or broadcast stations. And for example, foliage penetration radar used by military would usually have interference from some of these coexisting emitters. And the approach there was that they will just notch out the interference in the receiver, the result of which is there will be signal distortion, and because you're not using certain bandwidth, there will be loss of resolution as well. But in FOPN radars, the bandwidth was so wide that you could actually notch out the interference without an appreciable degradation in the performance. However, with the advent of mobile communications as well as new applications of radars, for example, automotive radars, nowadays pretty much every IEEE band has some kind of communication services, either partially overlapping with the radar transmission or sometimes, for example, in millimeter wave band, when it is unlicensed, it is free run for any kind of emitter. So this has become a huge problem now. So DARPA, there have been several programs by governmental bodies to actually address this problem. So DARPA about 10 years ago had this program SSPARC, which was about spectral coexistence between S-band communications and S-band military radars. And later on, NSF and some of the programs were mentioned in the previous talk. NSF then had this year's program where they started investigating spectral interference across all bands. And then there have been several other iterations of those kind of programs like SWIFT, PAR, and so on. So, and nowadays, a lot of other societies, especially within IEEE and including in ITU, people have become very cognizant of this problem. As a result, there has been an explosion of research in signal processing, communications, aerospace systems on how to address spectral congestion or spectral crowding or spectrum sharing between radar and communications. So broadly, two kinds of solutions have emerged. So this is a very broad picture. I'll go into some details in a bit. Depending on, so because we want to share the spectrum, one way is both radar and communications, they independently transmit or access the channel in the same spectrum, and then they have improved receiver processing technologies to mitigate the mutual interference from one to other. And in this case, the radar and the communications transmitter and receiver are separate, they are not shared. So this was something that was there in the early part of ISAC research, and we call this kind of paradigm as spectral coexistence. And if any one of either transmitter or receiver or both of them are shared, and in that case, there is probably a joint waveform that is being transmitted, then we consider it as spectral co-design. So spectral coexistence solutions were very good for legacy systems where we don't want to because of cost considerations, or we are unable to change the transmitter, receiver, or the hardware. In that case, we can do some kind of digital signal processing at the receiver for interference mitigation. But for the new systems that are coming up, we prefer spectral co-design where there's a common hardware, a common waveform, and there's a joint access of the channel. So obviously the more general version of this is subfigure D, where I give an example of a vehicular scenario where there is this red car, which is the transmitter for both communications and radar. So it sends a common waveform, a communications embedded radar waveform, for example. For example, it could be phase modulated continuous wave waveform. And then it goes towards the radar target of interest, which is the blue car. And from there, it gets scattered off and is received by the gray car, where the job of the gray car is not only to deduce the parameters of this blue car, which was the radar target, for example, its range, location, Doppler velocity, but as well as to decode the message, the communications message that was sent by the red car. So this kind of a bistatic co-designed system is more general. So I'd mentioned that vehicular applications are one of the major drivers of Isaac research, apart from many other applications nowadays. And this is an example from that kind of scenario. Obviously, this is a very broad categorization of Isaac, but in general, if we want to exhaustively see what other topologies exist, then you can classify them based on some of these metrics. For example, how radar and communications, they access the channel. Independent access, spectral coexistence. They may coordinate the access. Maybe radar and communication, they have some kind of information sharing between them, and radar accesses the spectrum for a certain time, followed by communications and so on, or what we call as opportunistic access of the spectrum. There may be a joint access, or there may be a shared access without actually any coordination of information between them. Then based on the hardware, we just saw whether it is the same or the common transmitter or hardware, based on the waveform. So you can take any kind of permutation and combination of different topologies listed there, and you'll get a new Isaac problem. And that's why when we look into Isaac literature, there are just so many variations of this problem depending on the applications. So a waveform could be separate, completely separate waveforms, a common waveform like communications embedded radar waveform, or there may be some kind of resource sharing in the waveform. For example, there may be a time slot, and certain time slots are used by radar, and then the rest of it is used by communications. Based on where these units are located, if they are co-located, that means at the same place, the transmitter and receiver, that is one configuration. And then we just saw the bistatic configuration. You can generalize it to multi-static or distributed or networked kind of system. And in that network, not all the nodes need to be identical. One could be phased array radar, another one could be a MIMO radar, or just a mechanically scanning radar. So it would be a heterogeneously networked environment. Then the performance or functionality. So you can have a radar-centric Isaac where the primary motive is to optimize the performance of radar, and communications is a secondary consideration, or it could be vice versa. And there we have joint radar communications where we do not prioritize one system over the other, but we are interested in the performance of optimal performance of both systems. And then we also hear this term dual function radar comms, where you have a transmitter or a base station that also performs the function of radar, but primarily it is a communications, wireless communications node. And then we have different specializations like MIMO radar, MIMO communications could be combined, in-band full duplex Isaac. Intelligent surface could be a part of the channel, and that could be also, this is something that is of more current interest. There's been a lot of research in past 1 year or so on IRS-aided Isaac. And then we have different other specializations depending on frequencies like millimeter wave, terahertz. They all have their own separate set of considerations while designing Isaac. So there are a lot of activities going on within IEEE. ComSoc has Isaac Emerging Technology Initiative, where there's a lot of researchers have come together on addressing this challenge in various ways or the other. In ERSI, where Commission C is concerned with radar and communications, and I'm a vice chair of ERSI Commission C. There also we have some working groups looking into Isaac problems. Signal Processing Society has a technical working group dedicated to this. Aerospace and Electronic Systems Society also has a working group for Isaac. So it is a very interdisciplinary area. Multiple societies are involved in this. So obviously, this is something that is very difficult for me to cover in this roughly an hour-long talk. I typically do a 3 or 4 hour tutorial to go into all the details. So I decided I'll cover a problem that is very recent, and we are looking into that problem these days, which is the dual blind deconvolution. And another interesting facet of this problem was that originally I got this idea from an APL engineer. He's not with APL anymore, he works for MITRE, but I met him in a conference in 2016, and he was working on what he called as dual deconvolution. And we have done a variant of that problem by calling it dual blind deconvolution. I'll get into this in a bit. So this was the motivation on Isaac problem and how widespread it has become now, both in research and applications. And there's a lot of interest in industry as well, as you saw in Misha's talk. And then we get into this dual blind deconvolution to understand a very difficult version of this problem of Isaac. And then I'll follow it by some of the lead issues related with dual blind deconvolution. And then if we have time, I'll close it with some of the emerging trends in Isaac that we have been looking into. Okay, so in this problem, so this is, like I said, you can do a lot of permutations and combinations of various topologies that I showed, and you'll get a new Isaac problem because there's just so many different types of communications and radar systems available. So here we look into one specific case where it's a coexistence receiver, meaning the transmitters are separate for radar and communications. And there is a common receiver. The radar signal gets reflected off from the targets, for example, some aircraft, and then it is intercepted by this common receiver. Similarly, communications signal is also being transmitted, comes through various paths, and it is overlaid or superimposed with the radar signal at the common receiver. So in this case, normally in radar problems, we know the transmit signal, we don't know the target information, and at the receiver, the goal of signal processing is to extract target parameters. But there could be some cases, for example, passive radar, where we also do not know the transmit signal. So both the transmit signal as well as the radar channel, so to say, or radar target information is unknown. In communications, it's the reverse. In conventionally, you can estimate the channel, and the goal of the signal processing at the receiver is to decode the transmit message. So the transmit signal is unknown. But then as we move to millimeter wave or terahertz, where the channels are extremely dynamic, whatever estimate you may have may very soon become outdated because the coherence times are very short for those channels. So in that case, both the channel as well as the transmit signal may be unknown to the receiver. And then when they are overlaid, when they're superimposed, then you have these 4 variables that are unknown: radar transmit signal, communications transmit signal, and their respective channels. So when all these 4 quantities are unknown, then how can we get information about both radar targets or communications messages? So obviously in each one of the problems, even though both variables are unknown, channel and transmitter, it is usually just one quantity that is really of interest. So in radar case, even though the transmit signal is unknown and somehow we would estimate it, but we are really interested in the channel information. And in communications, the reverse. We are really interested in the transmit signal information, even though the channel is also unknown. So this takes us to this dual blind deconvolution problem. So the very first equation that you see, if we look into radar receiver, then it's the transmit signal that is convolved with the target profile or the radar channel, and then it is intercepted at the receiver. So there's a convolution of transmit signal and the channel, both for radar as well as for communications. And then when you superimpose them, then it is a summation. So if in a classical deconvolution problem, you will have a product X and H, and you're observing it just through this convolved product, that is y, and one of the components is unknown. So for example, h is unknown, x is known, and we would like to know, we would like to do this deconvolution to find out h. When you have the summation like this, and let's say in radar case, we know the transmit signal, that is x, and in communications case, we know the communications channel, that is hc, then it is, because one of the quantities is known in both cases, then it is dual deconvolution, which was this problem that Masood Farsharshian, who worked for APL, that I came to know about this problem for him in a conference in, called Coursera, which was organized in Germany. And then with this Isaac problem coming up in the past few years, we decided to look into a more difficult variant of this problem where all 4 of these quantities are unknown. So that's why we are calling it dual blind deconvolution. Of course, you can have multiple emitters. There could be 3 radars and so on, and then it will become n-tuple blind deconvolution. I'll show it later that the solution that we propose could be generalized to even n-tuple case. We make some assumptions about the, so it's a ill-posed problem. That means if you don't have any additional information, you can, it's very difficult to solve. It's almost unsolvable. So it's ill-posed, which means that there could be multiple solutions that would map to the same YT. So we make some realistic assumptions about the problem. For example, the radar signal, we assume a pulse Doppler radar. So it is periodically transmitting a pulse train, and we can estimate its pulse repetition frequency, that is the interval or the periodicity of that signal. And there are ways to do a periodicity estimation. So let's assume we could estimate that. So we have the transmit signal, which is a pulse train. So we don't know S, for example, in this green box. And then we have a radar channel. That means there are, let's say, L number of targets. So it's a sparse scenario, which is also very common in radars. And each target is characterized by 3 unknown parameters. There is alpha r, which is the attenuation coefficient or reflectivity of the target, delay time or tau r, which is directly proportional to the range of the target with respect to the radar receiver, and Doppler velocity nu r. So these 3 parameters characterize every Lth target. And communication signal, we assume it is an OFDM signal. And the communications channel is also a delay Doppler channel, which is also common in some of these OFDM related problems. So this long equation at the bottom that you see is when I substitute all these specific models in the dual blind deconvolution equation mentioned on top. And then there are all these unknown variables. All the channel parameters are unknown. That is, all 3 parameters of each target is unknown, and same with the communication paths. And we don't know the signals S and G as well. So very difficult, very challenging problem. So to approach the solution of this problem, and we'll take some of the assumptions into account. These are very realistic. For example, channels are sparse. That means there are just few targets. Obviously, there isn't a target at every arrangement, because if there is, you don't need a radar. You can actually see, for example, there will be aircraft all over in the sky, but there are just few aircraft. So channels are sparse. The channel parameters, they're continuous valued. So an aircraft does not fly at, let's say, 300 meter per second or 400 meter per second in quantums like that. Its velocity could be anywhere between, let's say, 100 meter per second to 300 meter per second. It could be 101.5 as well. So they are not discrete valued parameters. These are continuous valued parameters that complicates things additionally. For example, you cannot use simply DFT to actually find out, to look into, for the Doppler velocity in the spectrum, because in that case, you'll have to bin the spectrum, which means you're assuming that these are discrete valued. The transmit signals, we assume they lie in low dimensional subspace. So here, there are certain representational bases that we could use. So S could be represented as BU, where B is a known matrix, and same with the communication signal. We assume this linear sensing model. So once you do this representation in low dimensional subspace, which is similar to lifting trick that is used in several ill-posed problems in signal processing literature, once you do that, then you can write the received signal as a linear model shown in this equation. The discrete signal model with the lifting trick can be written as follows. So y is equal to Aleph R in terms of matrix ZR, and then plus Aleph C ZC. So ZR and ZC matrices, these are rank 1 matrices which have all these unknown variables encapsulated within their structure. And then as you look into the structure here, then we see there are these exponentials like e to the power minus j2 pi, which is all coming from taking a CTFT of this signal. So it's a frequency domain representation. So for the time being, if we can recover ZC and ZR, we have all these unknown variables within those matrices. So the way we solve this problem is, so as I mentioned, ZR and ZC, they are rank 1 matrices. We have sparse channels, we have continuous value channel parameters, and we want to do this super resolved estimation, that is very near perfect recovery of these unknown parameters. This is something that reminds us of atomic norm minimization problems. So people who are familiar with L1 norm, so L1 norm of a vector is the sum of absolute values of the elements of that vector. Atomic norm, you can think of it as a generalization of L1 norm. It is an analog of L1 norm, but for arbitrary basis. So if the bases are rank 1 matrices, atomic norm will be the sum of the absolute values of coefficients of those rank 1 matrix bases. So we do this representation in terms of atomic norm for the signal that you just saw, which was expressed as a linear model in terms of rank 1 matrices ZR and ZC. And then we cast this as an atomic norm minimization problem shown in the box here. So we are minimizing the sum of atomic norms ZR and ZC. So ZR subscript AR and ZC subscript AC, those are the atomic norms of ZR and ZC, and their sum, because we are observing the signal as a superposition. We minimize this subject to the observations Y. So all we have are just those observations Y, and these assumptions, that is sparsity and continuous valued parameters. So atomic norm minimization is great when you want to recover continuous valued parameters, which a DFT kind of tool will not be able to handle. So what we saw was a primal problem. That means minimize the sum given this constraint, but I cannot go into the computer and actually code that thing up. I need a semi-definite program which computers can solve, and how to arrive at the semi-definite program of this primal optimization problem, we need to look into its dual optimization problem. So there's a primal optimization problem, and you can cast it as dual, and sometimes the dual problem will give you some clues on how to solve the primal problem. And if you have equality constraints, so we had equality constraints in the primal problem, like y is equal to the whole linear model. In that case, the solution of dual problem is exactly the solution of the primal problem as well. So we do this using optimization theory, go from primal problem to the dual problem, which is shown here. That is, if the primal was minimized, dual will be maximized. So you see the maximize Q, which is a dual variable, and then subjected to certain conditions on dual atomic norm. Even now, this is not something that I can program. It is not an SDP. So here there has been extremely beautiful work by several researchers, and there is a very nice book as well by Professor Bogdan Dumitrescu from Tampere University in Finland on positive trigonometric polynomials. So I had remarked about these exponentials that we saw in one of the slides. Those are trigonometric polynomials because you can express an exponential as sine and cosine. So when we have these, it turns out these dual atomic norm that you're seeing in the dual problem, they are positive trigonometric polynomial inequalities. And if we have these kind of inequalities, there is this very famous result in control theory that goes by bounded real lemma, where you can cast these positive trigonometric polynomial, we'll just call it PTP inequalities as a linear matrix inequality, which is this second last equation that you see. It looks very complicated, but once we get these LMI or linear matrix inequalities, this is an SDP that I can actually go into the computers and processors and can code it to get a solution of this dual blind deconvolution problems. So we get this semi-definite program, and now we can solve this problem using standard methods. So we have that solution, and then this whole solution that we saw, it is backed up by very strong mathematical guarantees. So it turns out once you get the variable Q, which was the dual variable, it is a multivariable polynomial, and you plot it in a delay Doppler plane, that is one axis, it's a function of range and Doppler velocity. So if you plot it in this range time or delay Doppler plane, it shows peaks of, so it reaches its maximum modulus of unity is reached when there is a target present at that range and at that Doppler. So that is what this guarantee says. And then it also mentions what is the minimum number of pulses you should intercept and minimum number of samples you should get, which is like, so M and then P are the number of pulses. What should be the minimum number so that there is a near perfect recovery? So once we plot this, as you see, this is how the dual variable looks, and wherever it assumes the value of unity, its modulus, that's where you can localize the targets in the delay Doppler plane. And we did these experiments for closely spaced targets and then randomly spaced targets. There are multiple variations of these experiments that we did. You can find the details in the paper here. So this is broadly the framework of how to solve this very difficult dual blind deconvolution using theories of positive trigonometric polynomials. So the beauty of this problem is it comes from an actual application, but the tools that are used to solve it, they are taken from optimization theory, from functional analysis and control theory, all of that coming together to actually solve a very applied problem. So this was a very simple model. I mean, if it already looks so complex, let's look into relaxing some of the assumptions that we made. So we look into some of the practical issues. So for example, so far we assumed that there was a synchronized transmission of, in the first version of this problem, we assumed that both radar transmitter and communications transmitter, they transmitted at the same time. However, this may not be the case in practice. There may be some delay between their transmissions. So if there is this lag between them, so here I'm mentioning in the graphic that is shown on my right side, the unsynchronized transmission, where there is a lag of tau e between the communications transmission and the radar transmission. So how can we apply the same theory now? So first we'll obviously have to estimate tau e. There are some ways in the literature when you can estimate this lag and then you correct for that lag and then solve this problem, the dual blind deconvolution. The method that we suggest is that we would estimate tau e jointly with this estimation of unknown parameters together. So we cast the problem in this way where this matrix E is a diagonal matrix that encapsulates this lag. So there's a difference between one of the properties of this lag is it is going to be the same between different pulses that you capture. So if it is going to be the same between the different pulses while the targets may be moving, then that is a property you can utilize or exploit to address this problem, and then proceed with the SDP formulation using theories from positive trigonometric polynomials. So we show here how that formulation will look like and can be solved using similar methods that I mentioned earlier. Then there could be multiple limiters like n-tuple blind deconvolution. So in that case, you will have as many linear matrix inequalities as the number of emitters you have. So if you have 5 radar emitters, 6 communication, then you are going to see 11 linear matrix inequalities in the SDP formulation. So it's very easily extendable to multiple emitters. So far we considered a noiseless scenario. Obviously there's going to be noise. So if there is noise in the received signal and you could estimate its variance, that is, we know that what its variance is through maybe previous measurements. In that case, you can take that into account as a penalty function in the optimization problem as shown in the SDP on the right here. Another interesting version is what happens when there are multiple antennas. This was just one antenna, but if we have a phased array receiver, and in that case, then the problem would become you have to estimate the range, the Doppler velocity, and now the angle, the direction of arrival as well. So we show that it's possible to incorporate this additional unknown parameter in the problem and then solve it using very similar theories. So in that case, our dual blind deconvolution model would look like this. So I'll just focus on the equation at the bottom where you see this parameter beta R and beta C, which are the DOA or direction of arrival parameters, which are also unknown apart from everything else that was unknown in the first version of this problem. And then we are here using NR antennas in the receivers. So when you have these additional parameters, at the same time, you also have now multi-channel measurements that you can exploit to actually solve this problem and estimate beta R and beta C. So we have very similar guarantees here. Again, the guarantee for recovery is that you look for the maximum modulus of unity while plotting the dual polynomial, and wherever it is unity in this now 3-dimensional version, in this hyperplane of beta R, that is direction of arrival, delay or range, and then Doppler velocity. So in that 3-dimensional plane, you have to find out this maximum modulus of unity, and wherever it is, that gives you the location of the targets. And similarly, we have the guarantee for how many minimum number of pulses, range samples, and receiver antennas you need to do a perfect recovery. And another practical issue could be there could be errors in the steering vectors. So if there is an error in the steering vector of the array, and there could be error in both gain and phase, you can actually take that into account in this formulation and then modify your atomic norm minimization accordingly. So far we have seen it's possible to extend this DBD problem to multiple antenna cases, multiple emitters, presence of noise, lack of synchronized transmission, and errors in steering vector. So it's fairly generalized to different practical scenarios. And there are more scenarios that we discuss in our paper. You can refer to that for details. So this is the steering vector error. Now the primal takes this form with 2 penalty functions, and then dual you formulate in a very similar way using theories of PTP. So it's very difficult to show this 3-dimensional plane in a graph like this. So what we have done here, we have shown it by keeping one variable constant and then plotted it for delay and Doppler by taking different values of DOA, and then we show that wherever it reaches the maximum modulus of unity, that's where you actually get the location of the targets. This was a framework where we refer to atomic norm minimization. So by no means that is the only tool to solve this problem. There are many other ways, and sometimes they give us deeper insights into the problem. So for example, one of the conditions for the recovery of parameters in the atomic norm minimization based method was that the targets, they should have certain minimum separation between them. And similarly, there should be certain minimum separation between the communication delays. And those, even though it's a joint problem and we are doing joint recovery, with atomic norm minimization, we could only guarantee this separation for radar and communications separately. But we were interested in, could we guarantee just one separation for communications to communications delays, radar to radar, and radar to communications? And in search of that kind of recovery guarantee, we started looking into Berling-Selberg extremization theory. So Berling was a Swedish mathematician, and while working on this problem, I came across this very interesting anecdote from his career. We were looking for good references of Berling's papers while writing this paper, and we were unable to find any. And then I read in Berling's biography published by American Mathematical Society that he rarely wrote any papers, but he gave a lot of talks, and his colleagues later on compiled the ideas from those talks in 2-volume books. So that's why this concept actually comes from that compilation of his talks, but it is very well known in the signal processing community, people who are familiar with these kind of problems. So the concept here is as follows. So here we are, this is something that we have just started looking into. So I don't have this generalized dual deconvolution problem that I discussed so far in atomic norm minimization framework. Here we are looking in a very similar problem, very simpler problem, where the radar and communications channels, they only have the reflectivity and delays. So no Doppler and no DOAs. And then we have this version of the DBD problem that is shown at the bottom after taking the CTFT of the received signal. So no Doppler, no DOA. Can we recover this? So we know from atomic norm minimization, indeed we can do this recovery, because atomic norm could do recovery of a much complicated problem. But now we want to solve this using Berling-Selberg majorant theory, and we want to come at this joint separation guarantee. So the way we address this is you can write, because you have all these exponentials, you can write this in the form of Vandermonde matrices, one for radar, one for communications, and collect all your unknowns in this vector called phi. So then I rewrite my overlaid receiver signal in terms of this Vandermonde matrix and multiplied by these unknown parameters. So in order to find out the stability of this problem in the presence of noise, can we guarantee the recovery? We need to look into the condition number of this combined Vandermonde matrix VG. So we have this theorem where we say that just this delta, which is a joint minimum separation, either between radar comms or radar comms delays, the condition number depends only on that joint separation. So if this kind of condition is satisfied, if delta, the separation is given by this condition, then we can perfectly, there is noise stability of this problem. So Berling-Selberg extremization, what it says is, so you saw this VG phi. So the received signal could be written in terms of Vandermonde, this generalized Vandermonde matrix VG, and then unknown parameters phi. So VG phi. So I expand it, and then I look at the norm of that received signal. It turns out that when we have these exponentials, then Berling-Selberg theory tells us that there are these functions that we call as Berling-Selberg majorant and minorant functions, which can bound these kind of functions on both sides. So if we can bound this, then the condition number is actually the max divided by the min. And if I have bounds for both numerator and denominator, in that case, I know this condition could be satisfied, the one that I showed in the previous slide. So this is an interesting result, because normally when you are working with atomic norm minimization, you want to, the goal is to look at the problem jointly for radar and communication. So even though we are doing a recovery jointly, the guarantee for recovery was separate. Now, this kind of theory actually allows for this joint guarantee. So that's what is the takeaway of this problem. And then for recovery, we use a different method, low rank Hankel matrix recovery, which is actually standard in the blind deconvolution literature. You can actually extend this to dual blind deconvolution problem as well. And then we have these numerical experiments where we show that this Berling-Selberg based approach, where we are using low rank Hankel matrix recovery, that can actually outperform atomic norm minimization. Now, of course, we have not yet generalized this second approach to DBD problem for Doppler velocities, DOA, and all those generalizations that I've shown you earlier. But at least in the delay-only case, this method gives better results than atomic norm minimization. Finally, I wanted to mention, so obviously I can't miss Battlestar Galactica, which is the favorite space shows for many of us. Finally, I want to mention some other Isaac-related problems that we have been working on. Some of the interesting ones. There are many others that I've left out from here, but you're welcome to catch me in a tutorial in Radar conference or any other conferences that I usually attend. I mention those tutorials in my LinkedIn feed, so you can follow the tutorial announcements there. But there are a few other trends. For example, there are sensor fusion-based approaches that are of interest, especially in automotive integrated sensing and communications, where radar and communications, they may have a common receivers, but the processing is done separately for radar and communications. And later on, using theories from sensor fusion, like Dempster-Schaeffer theory, you could actually combine the results to get an improved detection performance for radar. And I have provided the references here from our papers where we have looked into some of these. Misha had talked about privacy and secrecy. So we have the secrecy rate problems as well in DFRC, where you have an eavesdropper. So obviously when you're combining sensing and communications, radar is opening itself up to communications, and communications messages may also be intercepted by some other hostile entities. So if you have an eavesdropper present and you're doing this joint communication and sensing transmission, then how to minimize the transmission in the direction of eavesdropper? Those are the kind of problems that people have also looked into in secrecy rate for DFRC. Passive Isaac or distributed Isaac that I had alluded to in one of my slides. There's a lot of work in that area as well. These days, novel architectures are being looked into for terahertz, low terahertz joint radar communications. For example, how to manage this huge number of antennas at those frequencies that Misha had talked about. So you could employ hybrid beamforming. But then how to do that for both joint radar, both radar and communications is a problem that people are investigating. And a very recent development for past 1 or 2 years is use of intelligent reflecting surfaces for Isaac problems. You can use IRS, it's like a passive surface. You can mount it on the walls or on top of buildings, and all it does is the reflection, and sometimes it can do a few more functionalities. And if you have such a device mounted on walls and buildings, then how we can incorporate it for communications and radar separately as well as jointly is a problem that has generated a lot of interest in recent times. We are organizing an Isaac workshop in the 2023, the flagship conference of Signal Processing Society, which is ICASP. This year it will be held in Greece, and we have Isaac workshop there. And if anyone of you is interested in submitting your high quality papers, then the deadline is actually very close. But if you want an extension, please reach out to me and we can work something out. So please submit your papers here. And even if you're not submitting and want to attend, there will be a lot of keynote addresses by leaders in this area, and as well as panel discussions on the future of Isaac, so that may be of interest. We also have a special issue that I am co-editing with some of the colleagues of IEEE Journal of Selected Topics on Signal Processing, which is about use of machine learning for Isaac-based processing. And the manuscripts are due by May 15th, so I invite all of you to send your entries to this special issue. Finally, here is, I'm plugging my book here, upcoming book here on signal processing for joint radar communications, to be published by Wiley and IEEE Press jointly. It should be out in a couple of months. It's almost ready with some proofreading going on. And with that, I would like to thank you for the invitation as well as listening to my talk. And I'm here for any questions that you may have. Thank you.
Sir, how does the performance of this sensor get affected in the presence of other RF interference?
Yes, of course. So, I mean, communications is one of the interference that we are dealing with here. So by sensor, I am assuming a radar or similar, say even a passive sensor. So one of the problems that is almost immediately you can see in a radar or a radar sensor performance is the loss of resolution. Because when you have interference, then the usable bandwidth, because if there is a particular frequency at which interference is encountered, that frequency becomes not very usable in the receiver. And as a result, there is a loss of bandwidth. Loss of bandwidth leads to loss of range resolution as well as signal distortion. So that is something that is immediately clear, and then everything else carries forward in the processing chain. For example, your tracking would be degraded, detection, estimation performance as well.
Question from the floor, Ashutosh here. Excellent talk. I know you have a little bit of theory and practice. What you talked about reconfigurable intelligent surface, right? I think previous slide. That's a very interesting thing now. Do you have any bottlenecks there in terms of what is the challenge that needs to be solved? Have you looked into that?
There are many challenges, and I would love to come for another talk just on that, reconfigurable intelligent services. But just to summarize what we are currently experiencing is, so when you have, so you can use this intelligent surfaces in two broad ways. One, it could be a part of the channel. That means it is not co-located with the transmitter or receiver. So suppose I mounted it on the wall for indoor communications or sensing, or it is on top of buildings or other infrastructure. So it's part of the channel in that case. And there its job is primarily as a reflector. So the transmitter sends a signal, goes to the target, comes back via the intelligent surface. And this is very useful for non-line of sight sensing and communication. So when the direct path to the target is not available, then the sensing can be done using these reflector surfaces. Same with communications. You can extend the coverage. You can also use it to cancel the interference sometimes and so on. The main challenge here is that the signal that you get in the non-line of sight case, that is very weak. So it's far weaker than the direct path, and then to extract useful information from there becomes very difficult. Similarly, this is just one surface, but in practice we'll have multiple such surfaces, and then there may be cross interference as well, right? So those are, and there are many other challenges that I would love to go into detail in a separate talk. And then there are implementation challenges. So there have been some implementations recently. So for example, NTT Docomo in Japan have actually demonstrated outdoor communications using metasurfaces. And then there are several startups. Greener Wave is one of them. There have been some experiments at university level as well, what they call as smart walls. Huawei has been funding a lot of research in this area as well, especially in Europe. The second way you can use this is where it is not a part of the channel, but exactly at the transmitter. And when that happens, primary purpose over there is that if you use a normal phased array, you have the antenna, you have a lot of backend digital as well as analog circuitry. If you use the surface at the transmitter, you can actually include some of the analog components within the surface. So what we call as programmable metasurface-based arrays. And that kind of research has been there for a while in the electromagnetics and antennas communities. Now it's just trickling down to signal processing and communications more recently. And there are several challenges. For example, apart from implementation, near field communication. So in near field, you don't have a plane wave front, you may have a spherical wave front, and then you get this range dependent beam pattern from where you want to extract useful information and so on.
I guess what do you see the biggest challenges for the implementations of these solutions for these ISAC problems?
Yeah, so I mean, obviously, from theory to practice, there's a lot of things lost in translation, right? Then you become more humble as you start implementing some of these solutions. That said, there has been work on prototyping in various research groups. People have demonstrated spectral coexistence, for example, that is relatively easier. But even joint radar communications, you'll find some groups. So, for example, ComSoc's ETI on ISAC, the Emerging Technology Initiative on ISAC, has a separate committee which looks into this prototyping work. And if you go on the website, you'll see like a list of prototypes that are available. From there to industry, as Misha mentioned, that we need more academics and researchers to look into this problem, how to turn it into something that is more usable. I would say that work is ongoing. People are very, very actively looking into these solutions. A lot of companies are interested into this. Nokia, Ericsson, Qualcomm, Huawei, all of them at some level are looking into this.
Do you see this as like a main bottleneck for getting to fully autonomous vehicles? Is this one of those main bottlenecks?
Well, autonomy has a lot of bottlenecks because we still do not have a fully autonomous vehicles running on the roads. Of course, there are trials going on, as you would have read in the news. This is one of the bottlenecks and a major one, but not the only bottleneck for autonomous vehicles. I want to be careful there because you can have an autonomous vehicle without this intervehicular communication, just a radar based, which can impart some autonomy. But yes, to achieve full autonomy where the vehicle is fully connected, this is something that needs to be solved. But there are so many things, right? I mean, better AI is needed for autonomy, which we did not cover at all in this talk. So one of the major bottlenecks, I won't say it's the only one.
Some activities we will be doing. The next seminar right now is scheduled for April 25th, but please stay tuned. And I think there have been a lot of questions about slides. The recordings will be available in ACM YouTube channel, as I said, so hopefully within a week or so. But then these are some of the things listed. I know right now we are we have a, what are the Meet Me thing, right? Right. So you're probably getting local meet, right? So you're part of that. Then we are also having Future Network World Forum in Baltimore. That will be November 13, 14, 15. And so if you're planning to come and join, that's an IEEE conference, but obviously ACM will have some roles there. You want to volunteer for anything for the ACM Baltimore seminar series, please let us know. We have been doing it Hopkins, APL, but we are also looking for other places. If anybody in the neighboring university like to host it, please let us know. One of the bigger conference like Mobicom, not 2023, maybe it'll be 2024 because they have to do USA then outside USA. So I mean, I think these are some of the things. If we go to the next slide, what you have. Yeah, so vote of thanks, I'll give it to Wale to talk about it.
Thank you, Ashutosh. Again, let's give one more round of applause to all the speakers for today. Thank you so much. Very stimulating talks. Again, I want to thank everybody who is there in the audience and people on the Zoom from all over the world. This is really, really encouraging. Our idea here really to bring all of us together to start thinking about how to change the world. And I hope you are benefiting from this in terms of collaborating and working together so that we can generate new ideas, new solutions to help humankind. And I want to encourage you, if you want to get involved, please get in contact with Ashutosh. He's very passionate about this, and it's going to get you, look at this as an opportunity for development, skill development and professional development. So if you have any ideas, please reach out to us, and we are really willing to work with you to make the things in a better way. So thank you again for coming, and we hope to see you in the next seminar series. Thank you, and bye-bye.
Thank you, yeah. Thank you very much. I also, these would not have been possible without help from Mithun Mukherjee, who is not here, but a lot of other people in the back end, and Ryan for taking charge of the Q&A, and all the people who came here. Please try to come on site. I know we are getting out of COVID, thankfully, so please do come, chance for networking. So with that, folks who are still there, almost close to 100, thank you for your patience, and please do come back. Thank you.